I'm going to be talking about a framework for understanding efficiency, and this is really setting the stage for the next 3 talks, where you have some great talks from scientists studying efficiency from experimental and modeling perspectives and showing recent results. So this presentation is just to get everyone on the same page and thinking about efficiency in the same way. So this work started as during my fellowship with Carbon to Sea Initiative last year, and since then a few of us have continued to put some work into it, so David, Jens, and Charlie, and you'll be hearing from Charlie next. Okay, so starting at the very beginning, what do we mean by efficiency? In a carbon dioxide removal or CDR context, efficiency is typically a metric of net CO2 removal. So how much CO2 did you remove from the atmosphere minus life cycle emissions? This is often interpreted as a percent net over gross CO2 removal. When we're in OAE conversations, efficiency is typically a metric of gross CO2 removal. So this is often described as this eta value, so that's the efficiency of CO2 uptake over time is equal to delta DIC, or the CO2 removal from the atmosphere into the ocean, per alkalinity added to the ocean. So just to drive this point home, this is gross CO2 removal. And so the reason in the OAE space we talk about efficiency differently is because it's quite hard to measure gross CO2 removal. For the quote unquote easier CDR pathways like direct air capture, you just have a flow meter and you measure the CO2 flowing. That's your gross. OAE, we need to try a little bit harder. So how do we measure efficiency or CO2 uptake with OAE? We likely can't measure CO2 uptake directly, at least outside of a small area close to deployment. So we have to estimate it with known added alkalinity and efficiency factors, or losses. I'll be referring to them in this talk. So this approach ultimately requires modeling, and we need to parameterize these efficiency losses with either mechanistic understanding or observational data, or a combination of both of them. So the talks you'll be hearing today show the efforts in parameterizing those efficiency losses. So where we're at now is there's been a lot of modeling efforts, mostly focused on air-sea equilibration. So this efficiency factor is often a shorthand for air-sea equilibration. So the plot on the right here is from a great study by Seaworthy with Carbon Plan. And on the y-axis, they show the efficiency, that's what it says right there, efficiency, over time for various locations of OAE deployment around the world. So each line is a different location. Some locations are super efficient. You can get up to maximum efficiency within the first year. Some locations are not very efficient. They kind of peter out at 0.3 even after a decade. So from these modeling efforts, we're starting to constrain efficiency, where some locations are 0.8, some locations are 0.3, and so we can start kind of designing our deployments a bit more optimistic, or optimized to optimize efficiency. So this is great. Modeling global ocean models, circulation models have shown us a lot, but there are other things to consider. So those approaches to efficiency typically assume no loss of alkalinity. In real world deployments with real alkalinity feedstocks, alkalinity can be lost by several mechanisms. So for most of this presentation, I'll just talk you through what those mechanisms are. So the first category of efficiency losses to consider is mineral dissolution. So the ultimate question here is how much alkalinity actually dissolves in the upper ocean if you're using a mineral feedstock. Once that alkalinity is in solution, you need to consider how stable is that alkalinity. Is any of it lost to solids instead of remaining dissolved? Then once you have a stable alkalinity source in your water column, you need to think about how much of that alkalinity actually reacts with CO2 in the upper ocean over time. So air-sea exchange considerations. And then finally, we get to kind of the thorny, interesting ones, indirect impacts. So how does alkalinity impact other biogeochemical cycles in the ocean? So we have here 4 different categories of efficiency loss pathways, and these make sense logically to think about in this sequential order from 1 to 4. In reality, there will definitely be feedbacks between all of these different loss pathways, but I think as a mental model, the sequential order makes sense. So I'm going to be talking about each of these in a bit more detail and kind of subcategories within these categories. So the first category of mineral dissolution, there's actually two different considerations to think about. So the first is mineral dissolution kinetics. For most minerals, we have an idea of how fast they dissolve, ideal dissolution kinetics. But in the environment, actual dissolution may be slower than expected or incomplete. And this deviation from ideal kinetics is due to local conditions, hydrodynamics, environmental factors, and the quality of the mineral itself. For any OAE deployments in an open ocean environment, we also have to think about mineral sinking. So if you have a slowly dissolving mineral and it sinks quickly, you're essentially just dumping alkalinity into the bottom of the ocean and exporting all of it instead of having it react. So I'll show you on the next slide that models of mineral sinking show wildly different results depending on what you consider important in the model. But the takeaway for both of these is that current models that we tend to use by default don't accurately constrain these losses, and we need more observations to figure out what types of models are necessary. So this is an example from mineral sinking. This is a study by Yang and Timmermans showing magnesium oxide dissolution and sinking with different model approaches. So this blue line shows the Stokes settling velocity. And if you consider a particle of 10 micron diameter, about 40% of that particle will dissolve before it sinks out of the mixed layer. If you consider more complex models with turbulent shear velocity, almost none of it will dissolve before it sinks out of the mixed layer. So here we have two different modeling approaches. One shows effectively 0% efficiency, and one shows 40% efficiency for this modeled scenario. So this is an example of we need models to estimate this, and we need to figure out where the reality lies and how complex of a model we need to actually estimate this OAE approach. All right, so moving into mineral precipitation. This loss category is also commonly referred to as stability considerations or instability. So if you oversaturate a water body with too much alkalinity, some of the alkalinity will nucleate and precipitate out of solution back into solids. So this also depends on environmental conditions as well as the type of mineral. And we are starting to learn from research over the last few years. A lot of great research is coming out of Jens Hartmann's lab, showing that there are very clear thresholds for when this precipitation will happen. The thresholds do vary. So for equilibrated conditions, you can add up to 3 millimolar or upwards of 3 millimolar alkalinity. But if there are nucleation sites like plankton in the water, that threshold is lowered. And then if you're using just unequilibrated alkalinity for long periods of time, you have an even lower threshold. So these are just kind of ballpark examples. But the point is, we know what the thresholds are. We're starting to figure them out in different seawater environments. And so these losses may be easy to avoid with well-designed deployment. And we figured this out by recent research. I will note that you can also have mineral precipitation occur in sediments, and that's a completely different consideration because the thresholds in sediments are certainly different than they are in the water column, because poor water conditions are very different than water column conditions. There are very few published studies on this. Most of the studies have been considering olivine, but we really need more research across different types of coastal deployments. And then the third category is incomplete air-sea equilibration, or considering this air-sea flux processes. This can also be broken into two different considerations. So the first is the kinetics of air-sea exchange. So how fast does air-sea equilibration happen? We saw from that seaworthy and carbon plan plot that at some sites, the equilibration happens very quickly, and at some sites, it happens quite slowly. So we're starting to understand that location matters, and that model parameterizations also matter depending on the site. So you can have different parameterizations for a coastal site versus open ocean sites. In addition to the kinetics of air-sea exchange, you also need to think about whether the alkalinity stays at the surface or is subducted. And the difference between these two loss considerations is the kinetics simply delay CO2 uptake, while subduction and mixing result in effectively permanent alkalinity loss. So current models, global circulation models, air sea flux models, capture both of these processes pretty well, but we're continuing to improve them as we better parameterize them for OAE-specific scenarios. And the fourth category is a suite of different processes related to biogeochemical cycling. So I'll talk you through each of these specifically to give you an idea of how they impact CO2 uptake. So the first category is decreased sediment alkalinity flux. So in all of these plots, there's a white side of the plot that is a natural, non-OAE current ocean. And then the purple side is if we add alkalinity to the ocean. So in a non-OAE scenario, sediments have minerals that dissolve over time and release alkalinity into the water column. So that's a natural source of alkalinity. If we add alkalinity to the water column, we're buffering the water, and then sediments, minerals and sediments dissolve more slowly than they would otherwise. So they return less alkalinity to the water column. So the net result of OAE is we've suppressed a natural source of alkalinity. And then this, in effect, reduces the additionality of how much alkalinity we added intentionally. So we're reducing the additionality here. So that happens in sediments. The same thing happens in the water column. So that center figure there is referring to the carbonate counterpump. This is a natural process that occurs when calcifying organisms make their shells in the upper ocean. They die and they sink and they export that alkalinity into the deep ocean. So that's happening all the time. If we add alkalinity to the water column, buffer the water column, those shells will dissolve less as they sink, effectively exporting more alkalinity to depth. So the net impact of the sediment consideration and the carbonate counterpump consideration is the same impact where we are removing alkalinity or removing a natural source of alkalinity from the water column, reducing the additionality of our intervention. And then the fourth category is altering the soft tissue pump or the organic carbon cycle. So there's no inherent reason that we would think that OAE will move organic carbon cycling in either direction. So we just have this here as potentially altering the soft tissue pump. We need more data to understand which direction that this might go, if it has any impact at all. So the takeaway from these are there's currently very little data on each of these processes, but we understand enough about these systems that the losses are likely small. So I've said this on several slides, like we need more data. We don't know a lot about these processes. We need more data. So how much do we actually know? This is a plot of the number of studies that have been published on OAE-specific research on each of these four different loss categories. So as you can see, there are dozens of papers in each category. And as you'd expect, ocean modeling studies are the most numerous. These range from very local studies to global ocean modeling. And there are very few papers on indirect impact. So those bars are 1 or 2 papers per impact category. Importantly, all of these bars are growing. So the research in OAE is increasing exponentially in recent years. I know there's a lot of you in the audience who probably are sitting on data, just waiting to publish it, or in the middle of a research project, making these bars grow bigger. We have 3 great talks coming after me that fall into that category. This is how much we know. Dozens of papers is not a lot, but I think the question that everyone is after and what Carbon to Sea wanted me to answer is how efficient is OAE? Like how much do each of these losses matter? And given this knowledge base, we don't have a comprehensive answer for how efficient OAE is, and it really depends on different deployment pathways. So I'll use this framework that I showed, these 4 different categories, to just give an idea of what we're starting to know about these different loss pathways. So based on the research that's been published so far, we can start to fill in the colors about this loss is important, this loss is not so important. So across OAE, I just wanted to make the point here that it's really method specific. Every one of these loss pathways depends on the type of OAE that you're doing. But based on recent research, we're starting to understand air-sea equilibration enough that, yes, you can have high losses if you deploy at that 0.3 efficiency site. But if you design your deployment correctly, choose the right sites, you can really minimize those losses. Indirect impacts are likely quite small. And then I'm going to show you 2 different method-specific considerations here, and these are informing the talks that are coming after me. So we have a talk on ocean liming and a talk on coastal enhanced weathering with olivine. So for ocean liming, mineral dissolution kinetics are really important, as well as stability in the water column or potential precipitation. If you deploy too much alkalinity in the wrong locations, you can get really high efficiency losses. But if you design your deployment correctly, you can avoid those losses altogether or to a maximum extent. For coastal enhanced weathering of olivine, you have different things to think about. So you don't need to consider particle sinking, obviously, but dissolution kinetics can result in very high losses compared to the current models that we're using. So we expect it to dissolve quickly. It may not dissolve as quickly as we think it does. The same thing with loss of alkalinity in sediments. And so I just want to highlight here that high loss just means compared to the current models we're using. And also, again, this is gross CO2 efficiency. This says nothing about the net efficiency of the process, considering life cycle emissions. So research that has already been published and that we'll see in these next conversations has really been informing where we need to focus our attentions in this efficiency loss framework. So the takeaway here is that losses vary by deployment type. We need to understand which losses matter for which types of deployment, and that we need observations from specific deployments to quantify these efficiencies and get us out of these color coding generalities. So the takeaways here are fourfold. First of all, efficiency metrics need to be clearly defined. In an OAE context, you need to say this is gross CO2 uptake, and there are other efficiency loss factors than just air sea flux. Second of all, most losses are poorly constrained because the literature base just isn't that big yet, but they're constrained to different extents. So we know a lot about air sea flux. We're starting to know more about loss to solids. The other loss factors need more work, but all of these we're learning a lot about them very quickly, and the research base is expanding very quickly. And then finally, all of these losses vary by deployment method and location, so we shouldn't be talking about the efficiency of OAE broadly, but the efficiency of certain deployment types. That is everything. I hope that this context helps set the stage for the next speakers who will be diving into these in much more detail than I did.